Let's check out Newton's first law and Newton's second law. Newton's first law is sometimes called the law of inertia. It says a body in motion stays in motion at constant velocity, and a body at rest stays at rest unless acted upon by a net external force. Newton's first law means that if there is no net force on a body, it cannot accelerate and therefore must move at constant velocity. This means the body cannot turn, it can't speed up, and it can't slow down. Let's check out this example where the net force is equal to 0. So net force equal to 0 means there is no net force, obviously. So one of the symbols we will be using is this symbol here. This is a sigma symbol, and it means you add up all the forces that are involved, and in this case, we want to say that they all equal 0. So in looking at this situation, we've got this physics book sitting on some table. The table is applying a normal force upward, and the force due to gravity is applying a force due to gravity downward. So because a normal force is equal to the force due to gravity, the object isn't moving. If we were to draw a motion map, it would simply look like this. A dot for velocity and a dot for acceleration, showing that there is no velocity and there is no acceleration. So what forces are involved? We already said the normal force and the force due to gravity. So here's how we would write this out using this symbol. The sum of the forces, both the normal force plus the normal force plus the force due to gravity is equal to 0. So one of those must obviously be a negative. The force due to gravity is pointing downward, so that is our negative value. Now, even like it says here, even though there are forces on the book, they are balanced. Therefore, there is no net force on the book. And that's where we get that symbol there for that equation. So is it possible for the net force to be 0 and yet the object moves? Let's check out this situation right here. So here's a book, and let's just assume it went across with constant velocity. So in that situation, going back to it, we would have and this object moving to the right, as we saw. So its motion map would look like this. If it was indeed moving with constant velocity, we would draw all these velocity arrows the same length, showing that the velocity is constant. But because the velocity is constant, the acceleration must therefore be 0. So constant velocity means constant 0 acceleration. So the object was moving to the right. So if we looked in the vertical again, if we looked in the vertical direction, we know that the sum of the forces in that direction, the normal force plus the force due to gravity, were equal to 0. Okay, we already mentioned that in the vertical, but now if we look in the horizontal, like we drew the motion map for, in the horizontal, the sum of the forces are once again equal to 0. This force of tension, because let's assume that this is a string, is pulling to the right. That force of tension plus this frictional force here, which in this case, since it was moving, we want to give that a kinetic frictional force because it was moving, were equal. Both of those two added up were equal to 0. And because we considered to the right as being positive, our kinetic frictional force is our negative value. So this is an example of where the object can still move, in this case move to the right with constant velocity, and yet these two forces, the force of tension and the kinetic frictional force, are both equal to 0. So there was that video again. Now, Newton's second law. Newton's second law says a body accelerates when acted upon by a net external force. The acceleration is proportional to the net force and is in the direction which the net force acts. So there's Newton's second law. Alright, so the sum of the forces, like we said before, that's the net force. The units are measured in newtons. The mass is measured in kilograms. And the acceleration is in meters per second squared. And a really important part, again, is this idea that both the acceleration, both of these vectors, the force vector and the acceleration vector, they must act in the same direction. Okay? Alright. Now, the Newton unit is broken down as a kilogram meter per second squared. The Newton is the force required to accelerate 1 kilogram of mass at a rate of 1 meter per second squared. And we're used to using pound, which is a British system. But in our class, we will be using the Newton. 1 pound is equal to 1 slug foot per second squared. Something you do not need to know. Alright, so what happens if the net force is not zero? So let's look at the horizontal direction. In the vertical, we already said, because it's not moving in the vertical, that the sum of the forces is equal to the normal force plus the force due to gravity, and that's equal to 0. So that takes care of the vertical, right? And in the vertical, we said that the acceleration is 0 and the velocity is 0. So there's our motion map. In the horizontal, if we look at this situation, in this particular situation, notice that the force of tension, if we assume a string is pulling it to the right, is a lot longer than this kinetic frictional force. So in the horizontal, we would say the sum of the forces, adding up the forces in the horizontal, we would have the force of tension plus the frictional kinetic force, and that would not equal 0. According to Newton's second law, it would actually be equal to ma. Okay, the mass times acceleration, and that would be the mass of the physics book. And this would be the acceleration of the physics book. So in this situation, we would have a velocity that would increase in magnitude to the right with an acceleration that would, in this case, would be constant. So this is what would happen if the net force in a particular direction is larger in that direction, in this case to the right, the acceleration must be to the right. So the acceleration for the object is always in the same direction as the greater force. And so this is what that would look like.